Okay, in Calculus BC, we're dealing with our last two lessons in Chapter 7, and we are streamlining them. 7.6, we're actually not doing everything that's in the textbook, really trying to focus on BC's, the AP's criteria for what would be on the test. So we're just trying to prioritize and only focus on that. But you're going to notice memorize. There's no way around it. You want to know these derivatives, and I don't have time to prove these derivatives, but down the road, if you're interested, you could read in the book, or perhaps in a future day I can help you. But look at this. Not the derivative of sine, but inverse sine. Inverse sine. Notice that we have a u inside, meaning that whenever you're seeing that, it's not really like a u substitution where you'd have an integral, but it is there to let you know that the chain rule occurs so very often. It's exceptionally rare to just see inverse sine of x. So very often you have something else inside of it. That's what u is. So you've got the inverse sine of u. What is its derivative? 1 over the square root of 1 minus u squared, and then you do the chain rule. Take the derivative of what's inside. The derivative of u with respect to x is du dx. Now, the derivative of inverse cosine, by the way, inverse cosine is also known as arc cosine. Very important for us to remember that. I hope you remember that from, and for all of these functions, if you see inverse sine of x, that is honestly exactly the same thing as arc sine of x. Long, long ago, there was a difference. Back when I was a student, if you had inverse sine, you were working in degrees. If you worked with arc sine, you were dealing with that arc length. That meant work in radians. Since my time as a student, things have become relaxed, and they're just no longer in that regard, where arcs mean you're in radians. They're used interchangeably. But take a look at what's happening for the derivative of inverse cosine. I'm so sorry. You're going to see it's exactly the same thing, except you've got a negative out in front. It's the exact same derivative as inverse sine, except you just pull a negative out in front. It's negative 1 over radical 1 minus u squared du dx. Now, what I'm about to say right here, these are important, but this next one, oh my goodness. Inverse tangent or arctangent, that by far is the most common and popular inverse trig that you're going to work with, either for a derivative or an integral. We'll talk about that in just a moment. It's also the simplest looking form. It just becomes, if you had inverse tangent of u, it's 1 over 1 plus u squared. And then we'll have du dx multiplied to it. Nice and simple. Guess what, though? You've got to have these memorized. The last one is probably the least commonly asked, but it's by far the strangest looking. And that's inverse secant. So if you take the derivative of inverse secant of u, you get 1 over, and wow, look at this, a u outside of the radical, square root of u squared minus 1, then chain rule. You do du dx. And of course, right now you could say, okay, well, what kind of problems are we going to be doing? You'll have a worksheet today. We'll get that out to you in a little bit. But of course, you're going to have some problems where you're going to do just basic derivatives. So inverse sine of radical x, guess what? You're going to follow the very first template up there. So you'd say, what's f prime of x? Well, let's follow it. I'm looking up here. You're going to go 1 over the square root of 1 minus, well, here's your u. Your u is radical x. So I'm going to say, here's my radical x, and that's squared. Okay? Then you're going to have the du dx, the derivative of the inside. Now, we've talked about the derivative of radical x right here. What is the derivative of radical x? It's worth memorizing. 1 over 2 radical x. That right there is the chain rule. You just took the derivative of the inside. And that's following that template of a derivative. We're not done. We'll have to simplify it. But is that making sense so far, I hope? Okay, let's go ahead and simplify. You'd say, well, I'm going to square a square root. I might say, what are you talking about? Well, right in here. You square a square root, the square root just goes away. And you could say, well, that's going to be this radical 1 minus x. And then you'd say, well, over here I've got times a 1 over 2 radical x. Look, 1 times 1 is just a 1. I've got a 2 outside here, but I have 2 radicals. And guys, that means you could combine them. I guess what I'm trying to show you, just a property of radicals. If I gave you radical A times radical B, it becomes radical A times B. What am I getting at? These 2 square roots, it's going to be right 1 radical, and then you could say 1 minus x times x, or if you'd like, you could just put the x out in front. There it is. That's the derivative of the inverse sine of radical x. We doing okay? The key is you got to memorize these templates. If you don't have these memorized, obviously, then you're in trouble. So you might want to make a flashcard for it. Take a look right here at example 2. This is so important. The inverse cosine actually is just inside another expression. And you're going to see that occur all the time where, yeah, you might need to take a derivative of an inverse trig function, but it might not just be that inverse trig function alone. Right here, you've got a chain rule within a chain rule, so to speak. You've got this 3 out here. I hope you're realizing we've got to deal with that chain rule first. We're going to bring the 3 down in front. Then I'm going to say 1 plus inverse cosine of 3x. What's my new power? 2. And now we're focusing on this chain rule. We're going to say take the derivative of this inside part. And this derivative of the inside part right here, so the derivative of 1 goes to 0. But now you're going to come to this template. It's just like the problem that we just did, but there's going to be a negative out in front. So you could say negative 1 all over the square root. And by the way, here's your u. Your u is 3x, right? You could say, well, this is 1 minus, well, my u is 3x. I'm going to put that in there and square it. But then don't forget, you also have to deal over here with that chain rule. You got to deal with the derivative of du dx. And what's the derivative of du dx? What's the derivative of that 3x? Just a 3, right? So, finishing that up, this is your du dx right here. Right? If u is equal to 3x, du dx is just the 3. We doing okay? Now we clean it up. You could say, well, I've got a negative 1, I've got a 3, and I've got a 3. And that's going to become a negative 9. Also up on top, I've got this 1 plus inverse cosine of 3x, whole thing squared. And then down below, I've got this 1 minus, well, 3x squared becomes 9x squared. And wow, look at that. So these can get involved, but it's thankfully just a lot of practice on working through your chain rules and just making sure you know how to work through that template. Okay. Are we doing okay with that? Let's real quickly take a look at what I consider definitely to be the most complicated looking kind of an inverse trig derivative. This cube root of x is really x to what power? The 1/3. And you could write it that way to help yourself out. But follow that last template, and you're going to see that it's really involved. It's this whole thing here, and then you got to deal with your chain rule. Okay? So let's go ahead and see what we've got. We're going to have 1 over, and remember how that template's looking. It's 1 over u squared minus 1 du dx. That's kind of like what we're following. So I'm going to go 1 over, and I've got my u. That's x to the 1/3. Then I've got my square root. And then I'm going to have my u, which is x to the 1/3, but I'm going to square it. Then I'm going to say minus 1. But then we've got to clean it up. We've got to do our du dx. What's the derivative of x to the 1/3, guys? 1/3 x to what new power? Yes. Now look at what has just happened with that chain rule, with this right here. This is really something, and I'm going to break it down a little bit just to show you that, yeah, that first part, we just got x to the 1/3. You know, inside the radical, I guess you could just call it x to the 2/3. But look at this. This is going to be 1 over 3 x to the 2/3. Look at that. See what I'm talking about? And then you could say, well, why'd you do that? Well, I'm just breaking it down step by step. Guess what I really want to show you is this x to the 2/3 times x to the 1/3. That is a really cool property in algebra. If you have x to the m times x to the n, it becomes x to the m plus n. And what's 2/3 plus 1/3? 1. So you still have a 3. Then you've got x to the first. And then look at that. You've got x to the 2/3 minus 1. Wow. What looks to be maybe the most menacing looking derivative actually isn't the ugliest answer that we've done so far. So it can surprise you sometimes how you can do a little bit of algebra and clean some things up. We doing okay with that? Okay, last one. And by far, this is the most popular. And dare I say, a lot of kids will just say it's also what I feel to be the easiest. Because what's the derivative of inverse tangent? It's 1 over 1 plus u squared. No radicals. That's wonderful. 1 over 1 plus, and then you'd say, well, what's your u? It's this, 3x minus 5 squared. But you still have to do your chain rule. You got to have your du dx. And if u is equal to 3x minus 5, what's du dx going to be? Just a 3. Yeah, I heard somebody say that. You got it. So this thing right here is nice, quick, and easy. Again, what's happening? It's 1 over 1 plus u squared du dx. Whatever's inside of inverse tangent, even if it's something like e to the x or another function, you're going to be able to always say 1 over that and then clean it up. We doing okay? So that's moving from a function and taking a derivative. Now, listen, we're actually streamlining some things. And for the integration, we actually only are going to hold you responsible for 2 integrals. The first one, I think what kids will notice, without a doubt, they'll see that this is inverse tangent. But I think what bugs kids a little bit is that there isn't a 1 inside of the integral. I think that just is screaming out to everybody. They're saying, well, wait a minute. You know, you could actually factor that out. You could factor out an a squared from that and then get a 1. That's the quick proof for how that could work out. And then as you do that, you'd have a u squared over a squared and so forth. But this right here, again, something that you'd want to memorize, you're going to have inverse sine of u over a plus c. The second integral that we're going to work with is inverse tangent. We're not even going to, I'm not going to give you anything with an inverse cosine. We're just going to keep it to these two forms, okay? But again, this one right here, oh wow, this is 10 times more popular. You're going to see this way, way more. And when you have 1 over a squared plus u squared, notice what happens. You get 1 over a inverse tangent of u over a plus c. And the u's there are definitely set up to help you with u substitution. Now, one more comment that I want to warn kids about. The first year I was teaching Calculus BC, and this was a long time ago. I'll never forget it because a student took a look and saw these two and then said, oh, Mr. Dobner made a typo. He meant to put 1 over a in front of inverse sine. You see what I'm getting at? Over here, there's a 1 over a, and for inverse sine, it doesn't have one. And this student was saying, oh, Mr. Dobner just made a typo or a righto, whatever you want to call it. And he said, hey, put 1 over a there. Please understand something. That's not a mistake. It really is these two forms. The inverse sine does not have a 1 over a out in front of it. Okay? Yes?
Why is that?
It would be, I could give you a rigorous proof to show you why. And you know, right now, take it on good faith. It would involve factoring out that a squared for both, and then you'd be able to see what happens as you progress and finish up the problem. If we have time, we can do that. Otherwise, I'd challenge you guys to try to say, if here's like a first step, you'd say, hey, you know what? I'm going to factor out a squared here. Factoring is the opposite of distributing, so it's actually dividing, right? And then kids will say, oh, Mr. Dobner, the square root of a squared, it's just a 1 over a. See, you did forget it. Actually, no, if you made a substitution, we wouldn't call it a u substitution, maybe call it a w substitution or something to just put it in. You'd be able to see that that 1 over a will get canceled out. Here, because you're going to have not just a 1 over a, it's a 1 over a squared, things don't completely get wiped out. So that's the super quick answer to you. Okay? Let's real quickly, though, take a look. This is such a fantastic problem right here. Example 5. You could say, well, how do you deal with this? Well, right now, this looks like inverse tangent. It looks like inverse tangent. It definitely looks like the second one. And tell you what, I'm going to rewrite this. I'm going to rewrite this like this. You see what I'm getting at? You'd say, well, why are you doing that? Well, because the template was 1 over a squared plus u squared du. It's 1 over a inverse tangent of u over a plus c. And from here, pardon me here, what you're going to see is that your a is 4. You see that? Your a is a 4. Really, right here, your u would be just an x. Some kids will say, do a u substitution. Technically, you could. It would kind of be silly to do it, though. You would just be trading names with your variable if you did that u substitution. Okay? But in any event, if you're going to follow that, you're going to say, well, if I know this template, it's going to be 1 over a, it's 1 over 4, inverse tangent of my x, which is my u, all over 4 plus a c, then you are done. That's it. Okay? So that's the nice one. That's the one you're going to see more commonly. For example 6, wow, as we've been going through this, I meant to write in some bounds. And please do that right now. Very importantly, example 6, I want you to see the indefinite integral, but I also want you to see the bounds from 0 to 1, a definite integral. So here's where we're going. Clearly, this isn't inverse tangent, right? This is not inverse tangent. I think everybody would say inverse tangent's integral isn't going to have a radical in it. And there are only 2 possibilities. Wow, will that help you out? That I hope is going to be a tremendous help to you. You're going to say, hey, you know what? I now know that this has to be inverse sine. And inverse sine doesn't have that 1 over a over it. But I want you to see something, and this is where we can really break this down. We're going to say, okay, look, I've got x up here. This bugs kids immensely, and I totally get it. The first time we look at a problem like this, kids are going to say, I don't think this is inverse sine or anything with inverse trig. Look, you got x up there. Your notes don't have extra terms in it. But look, this 4, it's really something squared. It's 2 squared. And now's the tricky part. You're going to say, well, that means I've got to have a u squared. And you see, that's really where we're going with this. You're saying, what is getting squared to have x to the 4th? And the answer is x squared. You see that? And kids will say, so what's going on? That's your u. That's your u. And that's why these integrals are written in that form. Yeah?
Remember in 5, could x not have been a? Like, why did we substitute?
Well, a is the constant. A is what we'd have for a fixed number that won't change. The variable, which will vary and change, that's what we're generally going to call u. So let a be the fixed number, and let u be the variable. Okay? All right. So let's real quickly see where we're going. Let's see where we're going with this. Right now, I'm going to say du equals 2x dx, and dx equals du over 2x. Then, hopefully, good things are going to happen. Look at this. I still have 2 squared. This right here is my u. And dx becomes du over 2x. So good things are happening. Real good things are happening. And that once I've done that substitution, anything with an x has now been wiped out. And my problem only has u's in it. One last thing that we need to do, we need to change our bounds. Now, ironically, this is going to seem crazy, and it's very rare. Even if you forgot to change your bounds, you would have been very lucky, because when you change the bounds, they're actually the same numbers. Here, that does not happen hardly at all. Look at this. If x is equal to 1, that means u is equal to 1 squared, which is a 1. Wow, my upper bound changes to a 1. You'd say it didn't change. Yeah, you're right. Wow. You'd say, look at your lower bound. X is equal to 0. And u would be 0 squared. Wow. look, I think it's so critical to bring this up, though. If we're not really focused in on this, this is where kids could get tripped up. This is where mistakes could happen. And, it's very rare that these bounds are just going to be the same, right? So now what? We can say, well, I've got a 1 over 2 right here. And, wow, we are almost home. We are almost home here. We're going to follow that template right up here. And we're going to say, well, I need inverse sine of u over a. So I've got 1/2 out in front. Here's inverse sine of u all over a, because remember, your a is 2 here. And then I'm going to go ahead and go between those bounds. We doing okay with that? Almost done. Then we're going to say 1/2. We're going to have inverse sine of, well, plug in your 1, you'll get 1/2, minus inverse sine of 0. Now, at this point, I do want to remind you that inverse sine is actually going to give you an angle. Inverse sine always will give you an angle between opposite pi over 2 and positive pi over 2. I hope you remember that from AMA. And by the way, inverse cosine, if you wanted to know those boundaries, that was going between 0 and pi. And inverse tangent looks just like inverse sines, except you're undefined at pi over 2 and negative pi over 2. Right? So why am I bringing that up? You see, this is saying, give me the angle. When you've got inverse sine of 1/2, you're saying, give me the angle, and we'll work in radians here. And that angle has to be in the first or fourth quadrant, from negative pi over 2 to positive pi over 2. Give me the angle when the sine of that angle is 1/2. From the unit circle, the sine of what is going to get you 1/2? The sine of pi over 6. Yes. Right? Or 30 degrees, right? But we'd have that in radians, right? And then what angle would have the sine equaling 0? 0. And your final answer would be pi over 12. Half of pi over 6. Okay? So that's just some inverse trig review. All right, and believe it or not, we're trying to blend together some lessons right now. What I'd like for us to do is realize the rest of this lesson is going to be 7.8. 7.8, we are streamlining. We're going to keep this as focused on what the College Board is asking. There are plenty more problems that we could look at. We're going to just keep it just to what you are accountable for in May. L'Hopital's rule will become your favorite method to evaluate a limit. It can take hard limit problems and make them very easy. It's a very cool method. So L'Hopital right here, suppose that f and g, you're going to have an algebraic fraction, right? You're going to have a rational expression, one function divided by another. Suppose that you can take derivatives of them, perhaps not including a value at c where a limit is approaching, but let's just say that you were getting some indeterminate limits, 0 over 0, or plus or minus infinity over plus or minus infinity. Normally, you just say, wow, I don't know what's happening. I don't know how to proceed. Here's the amazing part. What they're saying is, if you're getting 0 over 0 or infinity over infinity, you can transform that limit into a new problem. Just take the derivative of the top f prime of x. Take the derivative down below, g prime of x, and look at that new limit. If that limit exists, that's the answer to the original problem. Notice, too, this is not, I'm going to say this 2 or 3 times. This is not, and I repeat, it is not the quotient rule. That will really trip you up. Normally, when you have a fraction, I say take the derivative. You'll say, oh, yeah, the quotient rule. Low d high minus high d low all over low squared. That is not what we're doing. It's real simplistic. So here's how to do L'Hopital's rule. First off, please hear this. The College Board a few years ago really warned kids that if you don't show work appropriately, you're going to lose points. And I'm talking about this. Look, show the limit of the numerator alone. Just work that out. The limit as x approaches 0 of sine of x. What do you get? 0, right? The sine of 0 is 0. Show the limit of the denominator alone. As x goes to 0, 2x goes to 0. This means L'Hopital's rule applies. Watch. I do this, and many professors do this too. This is the way my professor showed me utilizing L'Hopital's rule. You can put a cursive letter L here. And that stands, hey, I'm using L'Hopital's. You'd say, well, what's L'Hopital's? L'Hopital's rule says, hey, if the numerator goes to 0 and the denominator goes to 0, then, hey, what's the derivative of just sine? Cosine. What's the derivative of 2x with respect to x? That's your new problem. Look at that. You'd say, well, why is that there? Well, I'll tell you what, it's not 0 over 0. If it's 0 over 0, you'd say, well, I don't know what that is. You look at this, you'd say, well, hey, I know what this thing is. Cosine of 0, what's the cosine of 0? 1. Your answer, this limit, you're going to get 1/2. Okay? So that is a game changer. You could deal with some very complicated, difficult limits, where in the past you just say, well, I just don't know how to do it. And L'Hopital's rule will become, without a doubt, your favorite method to work out limits. Now, take a look at example 2. I think this is important for us to take a peek at. And sometimes kids wrestle with what's happening with secant and with tangent. Just want to give you a real quick review on how to graph secant. First off, secant is the reciprocal of cosine. And hopefully you remembered in trig that cosine, you might say, why are you graphing that in a dotted format? Some teachers call this the ghost trace, and you'll see why. I'm not asked to graph cosine. I'm asked to maybe take a look at the graph of secant. And cosine starts up high at 1, but cosine of pi over 2, that goes to 0. And this right here in red is the graph of secant. Now, of course, you could go ahead and do this a different way. I just wanted to review graphing with you. But what am I getting at? If you're going to approach pi over 2 from the left, you're going to approach pi over 2 from the left, you could say, well, 2 plus secant of x. Well, where are we going? Look at the graph. What do you think? Yeah, you're going to infinity. You're going to infinity. Kids might say, oh, it's undefined there. Yeah, but from the left side, you're actually shooting up towards infinity. Likewise, you could say, well, what's going on with tangent? With tangent, I just want to show you this much. This can be helpful too. let's just say that I'm giving you the graph of tangent. The graph of tangent, you're enclosed between negative pi over 2 and positive pi over 2. Tell me what's happening when you're approaching tangent from the left of pi over 2. Where are you going? Infinity. That means L'Hopital's rule applies. Because the numerator is going to infinity, the denominator is going to infinity. Okay? That means you can do L'Hopital's rule. And let's go ahead and see what L'Hopital's rule is going to look like. So, real quick, if I just had 2 plus secant of x, down here we've got 3 tangent of x. I'm going to put this cursive letter L here and say, hey, I've shown you that I checked if L'Hopital's rule applies. What's the derivative of 2 plus secant x? What do we get? Secant tangent. The derivative of secant is just secant tangent. Hey, what about and the derivative of 2 goes away. Hey, what's the derivative of just tangent? Secant squared. Now, it's usually at this part where I think kids can correctly wonder if really we're any better off. Right? Because if you're looking at this right now, you could definitely say, I'm not so sure if this really got better. First of all, look, it did. Secant and secant squared, you're just going to have a secant down here. Here's where a student could say, Mr. Dobner, I saw that a mile away. You're still in the same problem. You still have infinity over infinity. Right? You're still dealing with something infinite over something infinite. Aren't we no better off? Actually, I'd say we are better off. Here's why. Here's why. Look at this. Right now, yeah, it looks like we're no better off, but I'm going to say here's 1/3. Secant, if I bring it up to the numerator, what does it become? Cosine. And how about tangent? What could I rewrite tangent as? Sine over cosine. Wow, look at that. And all of a sudden you'd say, well, if I plug in pi over 2, I've got 1/3 sine of pi over 2. But what's the sine of pi over 2? It's 1. 1/3 times 1, you'll get 1/3. Look at that. Where did I get the cosine from? Well, a couple of ways you could look at it. Secant is 1 over cosine, and if you're dividing by a fraction, you're going to multiply by the reciprocal, right? But when you bring secant up, it's like you're taking the reciprocal of secant. And what is the reciprocal of secant? It's cosine. Right? So, I mean, either way you look at it, see, here's why I just wanted to show you. I think kids could understandably get upset and say, we're in a deadlock. You're no better off after doing your derivatives. You still have the same problems. You still have secant. You still have tangent. Aren't you still going to have infinity over infinity? How did it actually get better? You lost this addition right here where all of a sudden you could move things around. All right. So let's take a look here. Wow, this next one, what a problem this one is. What a problem this one is. Be careful with example 3. Be very careful. Kids will say, I already did L'Hopital's rule. Now, this is why the College Board is so emphatic about showing the separate work. What does this go to when you plug in 0? 1. Kids will say, what are you talking about? Well, look, 0 times the cosine of 0, that's 0 times 1. But what's e to the 0, guys? 1. L'Hopital's rule will not apply. Do you see what I'm saying? don't get into a mindset of saying, well, it's a limit problem, so therefore I'm going to do L'Hopital's. No. L'Hopital's rule does not apply. And that scares kids. They'll look at that, they'll be like, oh my gosh, well, what's happening? Well, your top is getting close to 1. Your bottom is getting close to 0, but it's a positive. Actually, you don't need L'Hopital's rule at all. 1 over something small is what? So this is positive infinity, done. Yes? Well, because 0 for the x, cosine of 0 is a 1, so that looks like it's 0, but e to the negative 0, see, e to the negative 0 is not 0. A number to the 0 power becomes a 1, right? So that's where you have to be real careful. And somebody could say, well, I did L'Hopital's rule, Mr. Dobner, I got this answer. That's where L'Hopital's rule is misapplied, and the answer that you get would be incorrect. So watch out for that. Watch out for that. That's why we always check. Speaking of checking, let's just come to this last one here. And we can say, well, check your numerator. Check your numerator here. We could say, well, we've got x minus sine x. And gosh, what's that going to be? 0 minus sine of 0 is 0. Right? The sine of 0 is 0. As x goes to 0 of x cubed, that goes to 0. L'Hopital's rule applies. L'Hopital's rule will apply. So what are we talking about? Hopefully we're going to be in a better place here. What's the derivative of the top? Help me. 1, and the derivative of sine is cosine. How about down below? 3x squared. And kids will say, oh, hooray! Bad news, guys. You still get 0 over 0. You see what I'm talking about? You'd say, oh, the top is 0. Oh, but so is the bottom. You see what I'm talking about? You could say, look, we're going to do L'Hopital's again. Look, cosine of 0 is 1. 1 minus 1 is 0. You'd say, well, gosh, 3x squared, well, that's just going to be a 6x. And you'd say, well, gosh, I mean, so sorry, that's going to 0. My gosh. Sorry about that. L'Hopital's one more time, perhaps? Or do we have to do 2 more times? Let's see, what's the derivative of 1 minus cosine x? What do we get? Sine. The derivative of cosine is negative sine. Negative, negative becomes a positive. How about down below? What do we get? 6x. Oh my gosh. I still have 0 over 0. But if you're on your toes, you know we're only going to have to do L'Hopital's rule one more time. Why? Because, yeah, we still are getting 0 over 0. You still are getting 0 over 0. So one more L'Hopital's. And now what? Your denominator, what's the derivative of 6x? 6. Derivative of sine is cosine. We're not going to have indeterminate forms anymore. Plug in the 0, cosine of 0. What's the cosine of 0 again? You get 1 over 6. And that's it. Guys, we're going to skip that last problem in the notes. That's all we've got for today.